Hey guys, it's Miss Johnson. I'm here to bring you our second notes for Unit 6. Today we're talking about binomial inequalities. So we're doing a little bit more of what we did in Unit 6 Notes 1, where we're combining multiple numbers of successes in our binomial experiment. But we're still talking about a binomial experiment, which consists of n repeated trials. Each trial has only two outcomes, one success and one failure. That's what makes it binomial. And then the trials are independent of each other. One trial does not affect the next. All of our notation is still the same. N is our number of trials, X is the number of successes, P is the probability of success on each individual trial, and then Q is the probability of failure. But remember that Q is also the same thing as 1 minus P, and some people just refer to it as 1 minus P, because if you think of 100%, you have one success, one failure, so the two together make up 100% of your trials. That's where that 1 minus P comes from. So binomial distribution is listed in that table that you all have. Hopefully you're looking through that big chart, that big table. We're still going to use that table again today and throughout the next couple days of Unit 6. All right, so let's take a look at example 1. It says a binomial experiment is repeated n times. Find the probability of X successes given a probability of P on a given trial. So what we want to do in this section is we want to pay attention to the inequality symbol that we're looking at here. So in part A, it says my n is 7. So I'm in that 7 section, that 7 box. It's on the bottom of the first page. I want X to be less than 2, which means that I'm taking 0 plus 1. 2 does not count because it's not less than or equal to, it's just less than. And then the probability is 0.3. So go to the 0.3 column, and then you're going to add up the 0 plus the 1, which is 0.082 plus 247. My decimal point was up high there a little bit, 0.247. All right, so then find your calculator. I'm going to grab mine, open it up. I got 0.082 plus 0.247, and I get 0.329 there for probability in that situation. In the next one, I have an n equaling 11, so I'm going to flip to the box that has 11 trials. So that's 11 trials of the experiment, and I want X to be greater than or equal to 6. That means I want 7 plus 8 plus 9 plus 10 plus 11. My probability of each individual trial is 0.7. Oh, and I'm sorry, hello, I need 6 as well, because this is greater than or equal to 6, so 6 is also a success. So I'm adding all of those together. So in the 11 box, which is the top of the third page, I go over to the 0.7 column, and then I'm going to go down to the row that is 6, and I add everything on down from there. So that's 0.132 plus 0.220 plus 0.257 plus 0.200 plus 0.093 plus, I ran out of room here, sorry, 0.020. So then let's take a look at what that adds up to be. And if I plug all those into my calculator, 0.132 plus 0.220 plus 0.257 plus 0.200 plus 0.093 plus 0.020, I get 0.922 there for probability. All right, let's take a look at the next one. N equals 5. So n is equaling 5 means I go to the 5 box, which is the middle of the first page. I want X to be greater than 2. That means 2 is not included. So I'm looking at 3 plus 4 plus 5. And then 0.95 is the column I'm at. So in the 5 box, middle of the first page, I go over to the 0.95 column, second to last column, and I'm looking at 3 plus 4 plus 5. So I've got 0.021 plus 0.204 plus 0.774. Adding all those up, I get a total probability of 0.021, 0.204 plus 0.774, 0.999 there. You could, oh, I already had an equal sign, sorry, 0.999. You could also look at that column, and the only probability that you're not including The first two are both zeros. The two successes is 0.001. So if you take 1 minus 0.001, you also end up at that 0.999. Either way would work, doesn't matter to me. Remember we talked about how you sometimes lose a little piece of accuracy in the rounding, but it's okay. If you show me your work and you showed me that's how you got your answer, then I would count it absolutely correct. All right, so let's go to the last example here. I've got n equaling 8. That's the top of the second page. I want x to be less than or equal to 5. So that means I'm going 0 plus 1 plus 2 plus 3 plus 4 plus 5. And my probability is 0.9. So I'm in that 0.9 column. Lucky for us, the first 4 of those rounded down to 0. So I have 0, 0, 0 plus 0.000 plus 0.000 plus 0.000 again. So that was 0, 1, 2, and 3. 0, 1, 2, and 3. And then the 4 success was 0.005. And the 5th success, or 5 successes, is 0.033. So putting those two together, 0.033 plus 0.005, because the other ones I don't need to add, I end up with 0.038. So there's our probabilities there. So again, just pay attention to these inequality symbols. Are you including the value or not? Are you greater than or less than? Don't forget about the zeros. 0 is one of your successes, or one of your possible outcomes, I should say. It's possible to have 0 successes, so you got to include that one as well. All right, let's take a look at our next example. In this one, we just have a few more examples of a similar situation, but this time we're looking at a compound inequality. So when we look at a compound inequality, our x is between two values. So in here, in part A, I'm looking at n equaling 7. So flip to your 7 box, which is the front of the first page. So I'm going to flip to the front of the first page of my table. Again, you can probably hear my paper shuffling around. And now I want 2 to be less than x, but x to be less than 6, which means that I want the 3 plus the 4 plus the 5. These are not inclusive. These are strictly less thans. So that means I'm not including the 2 and I'm not including the 6. I want the 3, the 4, and the 5. My probability here is 0.3, so that's the column I'm going to go to. So the 0.3 column, remember that those probabilities are also at the bottom of your table, which is really helpful. It's helpful to be able to see both pieces. So I want 3, 4, and 5 in that 0.3 column. So the 3, and again, follow along in the chart with me so you make sure you're finding the right values, the same values that I'm finding. So 0.227 plus 0.097 plus 0.025. So I'm going to add those 3 up in my calculator, 0.227 plus 0.097 plus 0.025. I end up with 0.349 for my probability there. Let's take a look at the next one. I want n equaling 12. That is the middle of the third page. So n equals 12. I want x to be between 4 and 8, and it's non-inclusive. So that means I want the 5, the 6, and the 7. I'm not including 4, and I'm not including 8. Probability is 0.4. So I go to the 0.4 column. I go down to 5, 6, and 7. The 5 column is 0.227. Oh, that was the same as the first one in the last example. 0.227, 0.177, and 0.101. So adding those 3, 0.227 plus 0.177 plus 0.101, 0.505 is my probability there. And then last one in this example, n equaling 10, bottom of the second page. I want x to be between 3 and 7, but this time it is inclusive. So I am including the 3 and the 7. So I need 3 plus 4 plus 5 plus 6 plus 7. Probability is 0.3. So go to that 0.3 column. I go from 3 to 7. 3 is at 0.267. So 0.267 plus 0.200 plus 0.103 plus 0.037, 37 plus, that was 3, 4, 5, 6, And then the 7th is 0.009. Add all those up. 0.267 plus 0.200 plus 0.103 plus 0.037 plus 0.009. And I end up with 0.616. All right, so those are the inequalities that are compound inequalities, or in other words, x is between two values. So just pay attention, is it inclusive or not? And then add up the values that are between the two values you want. One more example for today. It says a baseball player gets a hit 40% of the time that he bats. Suppose in the month of September he had 15 at-bats. Find the probability of the following. I want the probability of x equaling 10. So in this example, I know that my n is going to equal 15, and my probability is going to be 0.4 for each individual bat. So then what's the probability that he gets 10 successes? Exactly 10 successes. So I go to my 15 box, which is the last box of the table. It's the bottom of the last page. I go over to 0.4 for my probability, and I go out to x equaling 10. X equaling 10 is going to be 0.024. So check that out. Think of that for a second. Out of 15 at-bats, so 15 times that this guy stepped up to the plate, he has a 0.4 batting average. That's a really good batting average. If you're batting 400, that's a really good batting average. So out of his 15 at-bats, the probability that he gets 10 of them is 2%. 2%. That's why some of these baseball players get paid so much money, because when they can make that number of hits, getting 10 hits out of 15 at-bats, there's only a 2% chance that happens to them. So that's a really, really good batting average and a really low percentage that will happen. Anyways, moving on now, let's look at some inequalities. So now what's the probability that x is greater than or equal to 10? That means I want 10 plus 11 plus 12 plus 13 plus 14 plus 15. Quite a few values there. So I'm starting at the 10. Where's my 0.4 column? There it is. I'm starting at the 10, which is the 0.024 that we just found. Then I want the 11.007. Then I want the 12.002. And then the rest of those are all 0. So I don't need to add the 13, the 14, and the 15 because they're all zeros. So they're not going to make any difference to me. So let's add those three up. 0.024 plus 0.007 plus 0.002, and I get 0.033 for part B. Now let's talk about part C. So in part C, now you're looking at x being less than 10. So that means you would want the 0 plus the 1 plus the 2 plus the 3 all the way up to the 9. Now, it's not really that big of a deal to sit and add all of them. However, you already know 10 and above in part B. So the other thing that you could do is 1 minus the 10 up to the 15, which we know up above. So I could take 1 minus the 0.033 and see what I get. I get 0.967 there. So that's one way that I can find that probability. Now, I happen to have done this math before, and I know that when I add the 0 all the way up to the 9, this right here, I'll come down and make a new line here. The 0 all the way up to the 9 gives me 0.966, which is not exactly the same as the 0.967. But again, we talked about how when you're rounding these things down to 0, that doesn't mean they were actually truly 0. It just means that they rounded to 0. So somewhere between those last three zeros, the 13, the 14, and the 15, we lost 1/1000th of a point of accuracy. And that's okay. It doesn't make that big of a difference. It doesn't make enough of a difference for it to be wrong for us to do it this way. So this is a fine answer, especially if you show your work. This is also a fine answer if you went through and did all the addition of the other three. Both of those things work just fine. All right, so that takes us to the end of our video for today. Thanks for listening, and if you have any questions, let me know. Work on that practice assignment, and I will catch you next time.